this video, we're going to look at the mole, a chemist's best friend. Now, you can't survive the year without becoming best friends with the mole. Hopefully, this is a review from first year chem. You might recognize the mole as 6.022 times 10 to the 23rd particles, also known as Avogadro's number. This term mole, this unit, is used kind of like the word dozen. If I say I have a dozen donuts, I mean I have 12, a larger quantity. I could have 2 dozen donuts, and I mean I have 24. I could have 1 mole of particles. I could have 2 moles of particles. I just have a few more than 12 or 24. A mole is a ridiculously large number. I can't really wrap my head around how large this number is. It's something that I could never count, which is kind of sad and disappointing. But we have to have a number that's so huge to represent something that is so small. We use this number in terms of atoms and molecules, things that, you can't see with a microscope. They're just ridiculously small. Sometimes kids get the term atom and cell kind of mixed up. Like cells in a living organism are made up of billions and billions of atoms. Yeah, we can see cells under a microscope, not atoms and molecules. They're ridiculously small. The nice thing about this unit mole is that it lets me look at periodic table masses in terms of grams instead of AMU. When we were using AMUs and we saw that carbon had a mass of about 12, it's like 12.011. AMU, atomic mass units. That's when we were looking at kind of the atomic composition of carbon. 1 AMU is kind of arbitrarily the mass of 1 proton. So with carbon, if I'm looking at the mass in AMU, I'm usually thinking carbon has about 6 protons, 6 neutral neutrons, and that's where the majority of the mass comes from. And yeah, there are usually about 6 electrons. I'll put that down here just in case. 6 negative electrons. But the electrons usually don't contribute any substantial mass. So when I'm thinking about carbon being 12 AMUs, it's this. It's the nucleus, the protons and the neutrons. But if I'm going in the lab, I can't measure in units of AMU. I want to measure in grams. And it would be absolutely crazy to think that 1 carbon atom would weigh 12 grams. That's like saying a carbon atom is 12 paper clips. And again, that's kind of another misconception that people will have. Oh, well, that must be the mass of 1 atom. Hold on. Atoms are crazy, crazy, crazy tiny. 1 paper clip has billions and trillions and whatever comes after that. Lots of atoms. So this unit is so large, but it lets us represent a quantity of particles that we can actually manipulate in the lab. I could go in the lab and measure 12 grams. 12.011 grams of carbon. Absolutely, I could do that on the periodic table. But then I just need to be aware that if I've looked up the molar mass, which now we'll call it on the periodic table, that's the mass of a lot of particles. That 12 grams represents about 6.022 times 10 to the 23rd atoms. It's a way of counting atoms. It's a way of measuring ratios. So when we get to looking at balanced equations, if I need to do a chemical reaction and I need a 1-to-1 ratio of carbon to some other element, I can use this unit mole. If I need 1 mole of each, I'll have the same amount of atoms. Now, 1 mole of carbon and 1 mole of, let's say, oxygen would obviously not have the same mass. It's like comparing chickens and elephants. You could have the same quantity, but obviously they don't have the same mass. We're talking about different particles. So that's why we use the periodic table now as molar masses in grams. We can look up the same amount of particles, but we can get their relative masses, taking into consideration the fact that atoms have different sizes. The other little thing that we should mark down here And this will maybe pop up just a bit now, but more later on. 1 mole, 6.022 times 10 to the 23rd particles. That'll give us the atomic mass, or we may more often call that now the molar mass, in grams. Do you remember this? I guess it's a kind of a constant. 22.4 liters is the volume of 1 mole, any gas, at standard temperature and pressure. So again, we'll use this a little bit more when we get to the gas laws, but that's another constant that you may recall from first year. 22.4 liters is the volume of 1 mole, any gas, at standard temperature and pressure. Standard temperature being about 0 degrees Celsius, and standard pressure could be like 1 atmospheres or about 101 kilopascal. So we'll get into some of the specifics with this one in a few chapters, but it may pop up now, or it may just be something that's kind of convenient if you do remember this unit. Let's do some mole calculations here. Let's see what you remember from first year. How many moles of aluminum are equivalent to 10 grams? So I've got 10 grams, and one thing I don't like about this question is it just leaves it as 10. So for sig figs, I don't know if they mean like I rounded this to about 10 and there's only 1 sig fig, or if it really is like exactly 10. Hopefully you'd be okay with this. Can I put a decimal spot in there? Let's make it 2 sig figs. Let's say it was exactly 10. This is grams of aluminum. When I do mole calculations, I always set up a ratio or a proportion. I think this is the foolproof way of doing mole calculations. Now, by the end of the year, if you're so good at mole calculations that you can do it in your head, go crazy. But for now, if you want to make sure that you got the units in the right spot, you're converting to the right unit, I would highly suggest you humor yourself and write down the proportion. The unit that I want to cancel goes on the bottom. I don't want this in grams anymore. The unit that I want goes on top. I want it in moles. What an abbreviation. MOLE turns to MOL. Wow. All right, so now whenever I see grams, I'm doing a mole calculation, I see grams involved, I look to the periodic table. Now, you're probably going to be using the periodic table in your AP packet, so for the most part, we'll be looking at about the same amount of like decimal spots and all that. If you're using any other periodic table, I would never round these molar masses to less than 2 decimal spots. Now, the one in your AP packet, I like that periodic table because most of the masses are pretty reasonable. They're like, about 2 decimal spots. They're not crazy. So when I look up aluminum and I see 26.98, don't round it. Don't round that to 27. I get it. It's darn close. But there's a reason why the periodic table is listing it as 0.98. And in the AP test, they will want you to say 0.98. Don't round it. And again, if you do have a periodic table that's giving you like 3, 4, 5 decimal spots, which I've got a couple kind of old ones that I'm looking at now, well, then if you round it to 2 decimal places, I won't bite your face off. But if you're looking at the AP packet, most of them already are reasonable, like about 2 decimal spots. Leave it. Don't round them. That mass then that I find on the periodic table, if I'm using it in grams, it represents the mass of 1 mole. And again, I kind of freak out when it comes to canceling units. I find that really enjoyable. So grams and grams cancel. And then all I have to do is divide. Plug this in my calculator. And again, when we do sig figs at the end, this molar mass is kind of considered a constant. So I'm not going to use that when I round to sig figs. I'll go back to the amount of sig figs in the original measurement. So that's kind of why I wanted 2. I didn't really want to round this to just 1 sig fig. So let's call this 0.37 moles of aluminum. There, done deal. That didn't hurt so bad. It's all about the proportion. If you know how to set up these proportions, you don't have to memorize anything. You don't have to memorize, if I'm switching from this to this, I multiply. If I'm going from this to this, I divide, which is sometimes kind of a battle that I'll fight with kids. They just want a quick fix. Just set it up. Then you'll never get it wrong. Start with what you have. I have a little bit less than a mole of copper. 5.86 times 10 to the 23rd atoms of copper. And again, I would put in the unit. Not only would I start with the numerical value that they're giving me, but what is that? Is it grams, meters, liters, atoms, molecules, moles? Oh, it's atoms of copper. Then I'll set up my proportion. I don't want this in atoms anymore, so that'll go on the bottom. We want to know how many moles are equivalent. So moles will go on top. Then I just plug in the right ratio. 1 mole of anything is 6.02 times 10 to the 23rd atoms. Atoms on the top, atoms on the bottom. Moles is what I want. Now all I have to do is divide. And again, you could kind of make this easier on yourself. If this were multiple choice, and maybe by chance my calculator just died of batteries, it's a little less than a mole, right? 1 mole would be about 6 times 10 to the 23rd atoms. I got a little bit less. So I could estimate and at least pick a reasonable answer if this was maybe multiple choice. You could also make this a little easier on yourself if you're plugging it in your calculator and both of the exponents are times 10 to the 23rd. You can kind of cancel that. So in your calculator, you can just go 5.86 divided by 6.02. If they're not both times 10 to the 23rd, you can just plug them in your calculator or you can kind of simplify. But one note, if you are obsessed with the caret key, so if you're somebody that wants to enter this in your calculator as like 6.02 times 10 caret 23, that's fine. However, you will need to put these both in parentheses. So you can go 5.86 times 10 caret 23 divided by, make sure you put them both in parentheses. Otherwise, some calculators will do order of operations kind of funky, and you'll get some whacked out answer that's like times 10 to the 40 something power, and it makes no sense. So just a note, the best option is to use that EE exponent key. Plug this in as 6.02, then just hit that exponent key, EE, and then you just tell it times 10 to the what? 10 to the 23rd. That EE key is specifically used for scientific notation. So that means times 10 to the what? And then all you have to do is plug in, 23rd. Don't do this. 6.02 times 10, then hit the EE key, 23. Some people will accidentally use this kind of like the caret key. You're going to get an answer that's off by a power of 10. If you're using the exponent key, you don't have to tell it times 10. It knows that. It knows that you mean for this to be scientific notation. So just kind of watch how you plug this in your calculator. So if you don't get an answer of 0.973, 0.973 moles of copper, it's probably that you didn't plug it in your calculator correctly. So maybe try some of those little options down at the bottom. And that's totally reasonable. We said a little bit less than a mole. We could have something like this next one. Oh, man, milligrams. Yep. You might need to do a metric conversion. You might have to do like a milligrams to grams or kilograms to grams or something like that. The periodic table masses can be converted to grams, but it's not so slick working with this milligrams. So that's where I think it's kind of handy to remember these prefixes. Kilo, hecto, deca. Then comes the base unit. And then deci, centi, milli. I'm at milli, and I want to get this thing to grams. 1, 2, 3. So I'm going to do the same thing with my decimal spot. We'll move it 1, 2, 3, and we'll plug these spots in as zeros. Ooh, this is tiny. So I've got about 0.00568 grams of silicone. All right, what do we want to do with it? We want to know how many atoms are present. A few options. You could do kind of a one-stop shop with this. I do not want it in grams. I want it in atoms. All right, so whenever I need grams, I go to the periodic table. I look up the molar mass. 28.09 for silicone. 0.09. That's not the mass of one atom. That's the molar mass. That's the mass of 6.02 times 10 to the 23rd atoms. Notice, too, that I've been using 6.02 times 10 to the 23rd, and I think earlier in the study guide it listed 6.022. Either is totally fine. Let's see. We got grams on the top, grams on the bottom. You guys would be out. I'm switching it to atoms, which is exactly what I want. Multiply across the top, divide by the bottom, done. Now, your other option would be to make a pit stop at moles. You could say, well, this is 28.09 grams for every 1 mole, and then I could do another proportion where I switch from moles to atoms. But why string it out if you don't have to? Just be aware that the molar mass on the periodic table is not 1 atom. It's quite a few atoms. Now I can plug this in. My original number has 3 sig figs, so I'm going to leave 3. In scientific notation, whatever is out in front is significant. So let's go 1.22 times 10 to the 20th atoms of silicone. There we go. There's 3 sig figs. That's not so bad. I think I can handle this. The last couple. The mass of 4.86 moles of lead-2 nitrate. Ooh, fun. 4.86 moles of lead-2 nitrate. I have to write the formula. Lead's charge is +2. Nitrate is a polyatomic -1. This should be lead with 2 nitrate groups. NO3, 2. All right. We have moles, but we want mass, which represents grams. All right, so I always put my units in first because then I just go and find the right conversion factors. Whenever I see grams, I look at the periodic table. And if it's a compound, I do need to add. So I'm going to add this up to find the total molar mass. And you may remember, I'm going to need 1 lead. It's about 207.2. When I find the molar mass, do you kind of remember that you're going to have 2 times the mass of nitrogen and 6 times the mass of oxygen? Ooh, so this is going to be kind of a big boy. 1 lead plus 2 nitrogen plus 6 times the mass of oxygen. 331.22. And that's the mass of 1 mole. Whenever I use the periodic table, it's always the mass of 1 mole, even if it's a compound. 6.022 times 10 to the 23rd molecules of lead nitrate would be about 331 grams. This is going to be giant. Okay, so we plug this in our calculator and we get a huge number. I get, 1,000, like 609.729, la. Giant. Okay, so I've got a huge amount of sig figs on my calculator, but the original measurement was only with 3 sig figs. So I have to narrow this down to 3. And you have a few options. My personal favorite, scientific notation. Put it in scientific notation and leave 3 digits out in front. So I may round this to, how about 1.61 times 10 to the 3rd. And now this is in grams. There's one option. Your other option, you could round this and say like 1,610 grams, but do not put a decimal spot at the end. And then that shows me that the last zero there was rounded, which is exactly what we did. Either is totally fine. I kind of like the scientific notation better, but that's just personal preference. If you round it and leave the number in long form, just don't put a decimal at the end. The last one in this section is real similar. We've got the lead nitrate sample. We got the same amount. Let's see if we can find this guy. Oh, there's two more in this section. My bad. What would be the mass of nitrate ions present in this 4.86 mole sample? Now, there are a few ways that you could solve this. But if I wanted to kind of keep it with a little mole spin, let's start out with what we have. 4.86 moles of that lead nitrate. We want to set up a proportion, or we want to cancel moles. We want to switch it to mass in grams, but we only want the mass of the nitrate ions. Minus, or we could say -1. Ooh, fun. Okay. So here's maybe the easiest way to do this. Let's just find the mass of nitrate in this compound. Here's where all the nitrates are hiding, right at the end. So if we say 2 times the mass of nitrogen plus 6 times the mass of oxygen, I would be looking at about 124.02. That's the mass of just all the nitrates. Every one molecule of lead nitrate has 2 nitrate ions. Every 1 mole of lead nitrate is going to have 2 moles of nitrate ions. So we could just add up the mass of those 2 nitrates, and then that would be for every 1 mole of lead nitrate. Now I can just multiply straight across, round it to 3 sig figs. Oh, this isn't so bad. Let's say 603 grams of nitrate. Ah, nice. I like that. The last one listed down here throws this volume at you. And again, it's probably something that you'll see more often when we get to the gas laws. But if you can recall, 22.4 liters is the volume of 1 mole at standard temperature and pressure. It does make this a little bit easier. We've got 10 grams of oxygen. 10.0 grams. I do need to say 10.0 because that's going to give me 3 sig figs rather than just saying 10 and going to 2 sig figs. The other thing that we need to make note of, this is oxygen gas and he is diatomic. So if I wanted to turn this into moles, let's say I want to cancel grams, put it into moles. 1 mole of oxygen has the mass on the periodic table, but you will need to multiply by 2. Since oxygen is diatomic, its molar mass really will be 32.00 instead of 16. Now, if they were just referring to oxygen atoms, then I would just say 16. But this one says oxygen gas, and it's specifically telling me that oxygen is diatomic. Then I do need the mass of the 2 oxygens. So right now, if I wanted to, I could plug this in my calculator, and I'd be looking at moles of oxygen. But I just want to tack on one more proportion while we're at it. Why not? If I wanted to cancel moles, I could switch it to volume. Oh, yeah. 22.4 liters is the volume of 1 mole. Any gas at standard temperature and pressure. Moles, gone. Now we can just plug this in our calculator, and we're going to round it to 3 sig figs. which is actually kind of funny. This ends up as about 7.00. And then we'd say liters of oxygen gas. Often a gas would be measured in volume, like liters. So this would be a typical calculation that you might see with something like oxygen. Hopefully some of these mole calculations are familiar to you. You can give a few of them a try. And again, if there are any parts of this where you say, holy man, I never saw this before in my life, you might want to stop by for a little extra help. This should be mostly review. But I get it. It's been a while. So let me know if there's anything that's not coming back to you.